Hey everyone, my name is Ben, and in this video, we're going to talk about lakehouses and Apache Iceberg. But first, we're going to get some background info, and we're going to talk about data warehouses and data lakes. Here, we have a pretty standard setup. We have a application writing some raw data to a data lake. Now, the data lake is designed for huge amounts of scale, storing a bunch of raw data very cheaply, but it's not very good for querying or anything. To actually analyze this data for analytics, we need to move that data into a data warehouse. Data warehouse consists of three components usually. It has its own storage layer, which is structured. The data that's coming in here is organized into nice, neat rows and columns so that it can be queried easily. Then you have a query engine on top of that. This is where all the compute lives. This is what's translating SQL queries into manipulations on the data here, and it's also returning the results. And then usually you have some API layer. This is what users actually connect to. It's going to do authentication, logging, things like that. For what it's worth, I stole this piece of it directly from Snowflake's documentation. Right here, we've got the Snowflake architecture from their docs. You can see they've got cloud services, query processing, and database storage. All right, so you may be asking, why do we need data lakehouses? There's really two things wrong with this. Well, not wrong, but not ideal. The first one is that this data warehouse, even though it's made up of three separate components, it's really offered as a single service. It's an all or nothing kind of situation. If you get Snowflake, you have to use Snowflake's API, Snowflake's query engine, and Snowflake's storage engine. Same with Redshift. But you may not like Snowflake's query engine, or you may think that it's overbuilt for what you need. Snowflake is a really great, really powerful system, but not everybody in the world needs a super powerful data warehouse to run their analytics. They may be okay with something a little bit less performant and a little cheaper, and getting rid of all of these other layers that they don't need to pay for. That's one reason why you might not want this data warehouse. The second one is there's a little bit of duplication here. You see that we have a storage layer here in our data lake, and like I was saying earlier, data lakes are really optimized for low cost storage. They're super cheap, they're highly reliable, there's not a huge reason not to use them. But you have a separate storage engine over here, which is not nearly as cheap, right? The storage engine here for a data warehouse, to be fair, is going to be way higher performance. It's going to be lower latency, it's going to have higher I/O. But again, what if you don't need super high performance? What if you're going to be completely okay with a slower query as long as you can get really cheap data storage? So that's another reason why you might want to go with the lakehouse. So here we have a basic diagram of a data lakehouse. You can see that the inputs and outputs are going to be actually the same as before. We still have an application here writing raw data to a data lake. And on the other side, we still have a user making SQL queries to a query engine, right? But the differences are in the data catalog and the structured data here. So instead of moving the data into a data warehouse's storage engine, we're actually going to keep it in the data lake in object storage, but we are going to structure it so that it can be queried. So we have raw data in the data lake and we have structured data in the data lake. Now, to do the computation, we still need a query engine, and I'm actually going to call this a query/compute engine because those are separate things. And that's going to be what's actually serving our queries. And then the last step that we need, which didn't exist in the data warehouse, is a data catalog. Now, data catalogs are super common for data lakehouses, and they do a very important job, which is keeping track of all of the tables and data that exists in the data lake. Because a data lake is a very open ecosystem, there's a lot of files everywhere. You need to keep track of which files belong to which tables, and that's what the data catalog does. A lot of data catalogs also take on roles that are similar to the API layer in Snowflake. So they do access control, they do lineage tracking, they do auditing. So the data catalogs serve kind of the same role as the API layer. So some of the benefits that you'll see with the data lakehouse is one, low cost, because we're building the whole system on very low cost data storage on this data lake. We're not paying as much for the super high performance storage you'd see in a data warehouse. That is going to negatively impact performance. The other one is that you can really choose whatever query and compute engine you want. You may even have multiple compute engines. You can definitely run two different compute engines for different types of processing. It's very common to have a query engine for very fast queries and reads, and then a separate compute engine for very fast and efficient ETL, right? And they can both speak to the data that's in the data lake. And there's no problem with that. You could even have multiple compute engines that compete with each other on price, and you can really build a data warehouse or data lakehouse ecosystem that is really catered and fit to the needs of your business and your analytics workloads. And in this video, we're going to build a lakehouse using this set of technologies here. It's important to note you can build a lakehouse using any variety of technologies. This is just the one that I'm choosing for this video, mostly because all of these technologies are open source and free to use. For our object storage in our data layer, our data lake, we're going to use MinIO. MinIO is a very nice open source service that tries to mimic the API of Amazon S3. So you can use S3 compatible libraries, but point them to a local instance of MinIO running on your machine. For our structured data, of course, we're going to use Apache Iceberg. This is the open table format that's going to be the core of the structured component of our data lake. For our catalog, we're going to use Project Nessie. Nessie is a newer catalog that I really like because it's very simple. It doesn't have a lot of the nice bells and whistles that you'll see in commercial catalog offerings, but it does well enough just for a local demo. And we're actually going to run two different query engines or compute engines. The first one is going to be Trino. This is a fork of Apache Presto, which is their query engine. And then we're also going to run Apache Spark. Now, Trino is more for queries. It's more for reading the data efficiently and offering a JDBC compliant driver. Apache Spark is more of a compute engine. It's not really a query engine in that you can just send SQL queries to it directly, but it's going to be really good at ETL and transformations. So we'll be able to see that using the same core data lake with the raw data here and the Iceberg tables here, we can use whatever query or compute engine we want and really cater it to our needs. All the code for this project in this video is going to be available on my GitHub at github.com/bensivo/learning by example Apache Iceberg. You can see we've got a few different modules here corresponding to those different categories that you saw earlier. Object storage, catalog, query engine, compute, and a basic ELT job. So the first thing we're going to do is we're going to run MinIO, our object storage service. This is going to be the main storage layer for our data lake. It'll have the raw data and the structured data as well. Now in our repository in folder 01 object storage, you can see a compose.yaml. This is just a basic Docker compose. We're going to run MinIO right here on a container on port 9000 and a MinIO init container, which is going to create some buckets for us. One thing you'll note is that we have a hard-coded access key and secret key here, mimicking AWS's access key and secret key authentication. We're just going to run this with the minio.sh script. That's going to come up for us right here. So this is the MinIO object browser. You can see that we've got two folders from the MinIO init script. We have a raw folder, which is our data lake, and then the Iceberg folder, which is the structured portion of our data lake, or the data lakehouse. Next, we're going to look at the catalog portion. We're going to run Project Nessie. Once again, we're just going to run Project Nessie in a Docker Compose. We have that right here. Nessie runs on port 19120 by default, and we're just going to go into that folder and run nessie.sh to bring that up. It's going to take a few seconds. There we go. Here's the Nessie homepage. There's really not a lot here right now because we don't have any tables. The job of a catalog at its core is just to map from a SQL table name to the location of that table in the file system, so in MinIO in this case. And because we don't have any tables, there's nothing here to see. As we start inserting tables into our data lake house, we will see this populate. Next, we're going to run one of our query engines, which is going to be Trino. We're going to start with Trino because it's simpler, and then we'll go to Spark later on. Once again, yet another Docker Compose file for running Trino. It just runs in a single container. But there is one thing I want to point out before we actually run it, which is the configuration here. So we have a few properties files for Trino, and iceberg.properties is the important one. Trino is a very generic query engine. It's not made specifically for Apache Iceberg. It's not made specifically for MinIO. So we have to configure it and tell it what file format we're using and what our file system is, MinIO. So here you can see that we're configuring the catalog. We have iceberg.catalog.type is Nessie, and we have the URL to Nessie right there. And we have to tell it what the file system is. So here it's S3, but MinIO is an S3 compatible service. So you'll see we're giving the endpoint of MinIO and then our hard-coded access key and secret key. That's how Trino is going to know where to put tables, where to look for them, and then where to find the mapping between table names and the file system paths. And we're just going to run Trino using the trino.sh command. This is going to take a second to come up. And here we go. This is the Trino login page. We haven't really enabled authentication here, so there's not even a password, but you can just put admin, and we see the Trino UI. There's really not a whole lot going on here. This is more of a monitoring UI. As we start making queries, we'll see them pop up here, and we'll see some basic metrics about, right, like how many queries per second we're running, things like that. All right. Now, technically, we have a data lakehouse. That was it. We have object storage here, which has a section for raw and structured data. We have a data catalog in Project Nessie, and we have a query engine in Trino. So in theory, we have everything we need to start inserting data into our data lakehouse. And we actually can do that using the SQL Tools extension in VS Code, which lets us connect to Trino. So here in VS Code, I'm just going to go to my SQL Tools extension and add a new connection. I'll use the Trino driver. I'll call it Trino. Give it http://localhost port 8080. The Iceberg or the catalog is going to be called Iceberg. The username is going to be admin. Let's test that. We're good to go, and we can save the connection. So I've got a few SQL queries right here that are ready to go. First thing we have to do is create a schema. Just like any database, tables are organized into schemas. A schema is a group of tables. We're just going to create a schema. We're going to call it staging. And we're also going to put location here, which is a little bit different to traditional SQL. So this location is going to tell us where in the MinIO file system we want to store this schema. So we're going to give iceberg/staging. We'll just run that. And next, we need to create a table in this schema. So very simply, create table if not exists, staging.helloworld. We're going to give it a greeting and a name. We'll just run that. And finally, we're going to insert some records. So into that hello world table, we'll just insert 3 rows, hello Alice, hello Bob, hello Charlie, and we'll run that. So we've got a SQL database. Now, if we run select star, we should get those 3 records back. And we do. So we have something that looks and feels just like a SQL database. We can use SQL to interact with it. We can insert data, we can query data, but it's split up into these 3 separate components: the object storage, the catalog, and the query engine. Let's actually look into each of those services and see what is going on in the back end, which is enabling us to do this. So first, let's look at Nessie. This is our catalog, and we're going to see that we now have a folder here called staging. Remember, we created a schema also called staging. Inside that folder is going to be a table called Hello World. If we click on it, it doesn't actually have the data here. All it does is it points us to a metadata location. This is the location in S3 or MinIO where the table is stored. So let's go to this location and see what that table looks like. So in MinIO, we've got the raw files and the Iceberg files. Let's go to Iceberg, staging, and we'll see a table here called, or a folder here called Hello World. So we see a folder here called Hello World and then a bunch of random numbers, right? Sorry, go. We can actually look into this folder a little bit and see what it's doing. Inside of this folder is 2 more folders. We have data and metadata. Now, this is all specific to Apache Iceberg and how Apache Iceberg organizes the files. But the data folder is actually where the rows and columns are going to be stored. Iceberg uses Parquet under the hood to actually store the table contents themselves. And in the metadata section, we have a bunch of JSON files, a stats file, and Avro files. The metadata is going to store references to the data files, and it's also going to play a really key role in partitioning and helping in query performance. But at the beginning of this video, I was explaining data lakes and data lakehouses, and I said that data usually comes in from the application in a raw format, not in SQL format. So let's simulate that here. We have a basic generator Python application, which is going to generate a bunch of JSON documents with metadata and payload. This is simulating page loads events. So it's like a browser application. We're going to randomly generate pages, usernames, and browsers, Mozilla Firefox, Chrome, Safari. We're actually going to do segments of 1,000, and we're going to push tens of those. So we're going to have 10,000 JSON records that are going to be pushed to our data lake. We're just going to run this with generator.sh. So let's find the data that we just inserted. We can go into our raw section now, page load v1, and then it's organized by date here. So today is June 5th, 2025, and pull out one of these files. You can see there's 10 of them. Let me just download one of those and open it in VS Code. Here are the records, right? So this is all great. This is data that you could imagine was pushed from some application, but it's not in SQL format. How are we going to get this into our Iceberg table so that we can query it effectively? And to do that, loading and transformation, we're going to turn to the next component of our Lakehouse architecture, which is Apache Spark. Spark is by far the most popular distributed compute engine, and it's really great for tasks like this. Now, this video, I'm not going to go into all the details of Apache Spark. That's a whole series of videos all on its own. But all you need to know for now is that Spark is a distributed compute cluster. So it actually has a master node and then one or more worker nodes. Here we just have one of each. And we're going to write Python files. Those are going to be Spark jobs. And we're going to submit them to the cluster and they're going to execute them. It's worth mentioning in the Spark Docker file that we're running, we actually have a custom Docker file here. We're not just using the open source, freely available versions. We've got a customized installation of Spark, which has Java 11, Apache Spark, and then importantly, it has libraries added to it. So there's one library for adding Iceberg support. There's another library for adding AWS support. And you could imagine there would be another library for adding Nessie support, but actually Nessie is supported by default in Apache Spark. Just like before, we're going to run this with a basic script. Let that come up. And here's the Spark UI. This is again just a monitoring UI, but you can see that we have a Spark master node running in port 7077 locally, but we've mapped that to 8081. And then we have a worker node here. Right now, it's alive and there's nothing running. It's got 4 CPU cores, 6 gigabytes of memory, pretty small cluster. So here's the job that we're actually going to submit to Apache Spark. You can see that we just start with a bunch of configurations. Here, we're configuring that this is going to be using Iceberg as its main format, and it's going to be using Nessie as its main catalog. You can see catalog.type is Nessie, and then we have the Nessie URL. Next, we're configuring the file system. So this is the Hadoop FS S3A file system, and we've got the access key, secret key, the endpoint for MinIO there. And then we're going to use the spark.sql function, which lets us just write SQL in a string to create a schema, just like we did earlier in Trino. And we're going to use the spark.read function to load a bunch of JSON data into a data frame. Data frame is a table, essentially. And then we're going to write that to Iceberg format to the table staging.pageload_v1. And because we already set the location up here, that's how it knows where to store that table. So we can just run this job by running submit.sh and then give load.py. It's going to take a while to run. Okay, so now we should be able to use Trino to query the data that we just inserted into our lakehouse. So within Trino, we have the schema called staging. We have tables, and there's page load v1 right there. I can just show table records just like that. And you can see we have a table. You can see that loaded at and that loaded from column that we added, and metadata and payload. Now, this isn't super great. You can see that metadata and payload have this weird nested structure going on. That's because we were loading a nested object. In the next step, we're going to transform this data to flatten it out and make it easier for us to query. So here is the transform job. Once again, we have all of our Spark configurations at the top. And then in this case, we're using a lot more of spark.sql because our data is already loaded into the lakehouse. It's already queryable via SQL. So from now on, it's going to be a lot easier, if possible, to do all of our data manipulations just using SQL, right? We're going to create another schema. This one's going to be called model. And then we're going to use a create table to actually predefine the schema that we want. So here we have event name, event version, event timestamp, page username, browser, right? We're also going to say using Iceberg, and we're going to set a partition column. Now, partitions are really important in Iceberg. Iceberg doesn't have anything like a index like you would have in a traditional relational database. What it does have is partitions, which are very similar to indexes. If we put partitioned by event timestamp for this table, when Iceberg is saving the table, into files, it's going to split it by the event timestamp and then store them appropriately in different files like that. In the metadata files that we were looking at earlier, it's going to know based on the event timestamp which file a certain record is in. That's something like an index. So if we set select star from this table and we set a timestamp, it'll be able to skip entire files because it knows based on the metadata that that file doesn't contain the records that we're looking for. Continuing on, we just have a basic select query here. We're actually creating a data frame off of the table that already exists. You can see that we're selecting metadata.name and we're renaming it to event name. So we're creating a data frame that matches the schema we created in our other table. And then we're going to drop some duplicates, do a show, and once again, we're writing it using the dataframe.write function there at the bottom. Sorry, I can't use the mouse on this part. My hands are full. Once again, we're just going to submit that to the Spark cluster with submit.sh transform.py. Okay. And now, so looking at Trino again, we have a new schema here called model. We can open that up and look at the table. The table is called page load now. If we look at those records, you can see that this is now the transformed data set. So it's all the same data as before, but we've flattened it out. We've taken metadata.event name or metadata.name, turned it just to event name, right? This is a much more familiar format of the data. It's nice, neat, rows and columns. This is going to be way more useful for us for actually doing analytics, right? All right, so that is our open data lakehouse. We've built it completely using open source technologies, completely running just on my laptop here and a few Docker containers, nothing close to a production setup. But if you wanted to, you could turn this into a real production setup, right? The main benefit here is that your data exists in MinIO, and because it's using an open source standardized file format, Apache Iceberg, and an open source standardized catalog like Project Nessie, then you can really use any query engine that you want. You could turn them off at night so you don't pay for them. You could use Trino if you really want to do a bunch of queries. You could use Spark if you really want to do a bunch of computation and transformation. Really, it's all up to you, whatever you want to do with it. You just have to put forth that effort to actually maintain this whole system. But depending on your company, that might be the best thing in the world since sliced bread, right? The important bit is we have unlocked the scale. We've kept the scale and analytical processing that we had in a data warehouse. We still have the same level of scale that we had here, except it's much more customizable to our needs. Now, the one other thing to note is it's not nearly as performant, right? Compared to a data warehouse, which is a dedicated ecosystem built with every piece in mind, Lakehouse, it feels a little bit more like you're cobbling together a solution with Lego bricks, and the solution that you end up with isn't going to be super well designed and streamlined and cool and sexy, right? It's going to feel more like something you hacked together, but it's going to work. And the important thing is it's going to be cheap. You can build this whole system for very, very cheap, especially if you're not running a ton of compute on it. S3 is very, very cheap. And then the data catalog you can run on like a single VM. So you can make this whole system incredibly cheap for your needs, right? Thank you guys. I hope this video was useful to you guys. Once again, check out the repository here on my GitHub and hope you guys have a good day. Bye. Sorry about that.